We begin today with infrared spectroscopy. Last time we talked about mass spectrometry. By the way, if you want to tick off an analytical chemist, you need to talk to them about mass spectroscopy. They get really mad about that. Spectroscopy refers to absorbance of some kind of light. Mass spectrometry doesn't involve light, so they don't call it spectroscopy. Anyway, infrared spectroscopy tells you about functional groups that are in a molecule. And it's something that you will use if you take the Chemistry 353 organic lab. It's not the most powerful technique anymore for understanding the connectivity of organic molecules, but it's a quick way to check and see what functional groups are present in a molecule. So by infrared, here's your electromagnetic spectrum. We see in the visible range, infrared is just below that in frequency, lower energy, and a little bit longer in wavelength. So we could talk about the kinds of photons that are accounted for in infrared radiation. The wavelength of light that's sort of considered to be in the infrared is from about 2.5 to 25 micrometers. That's in wavelength. Wavelength is a convenient set of units to deal with, though if you remember from physics that wavelength and frequency are inversely proportional, the frequency of light that corresponds to this range of wavelength is much less convenient to write, 1.42 times 10 to the 14th to 1.2 times 10 to the 15th hertz, which is units of per second. Now, you need to, why are we doing this? It's boring, but you need to understand the weird units that we tend to use for infrared spectroscopy. We use not wavelength, nor frequency, but we use something that looks like frequency with a little tilde, and that number is equal to 1 over the wavelength. And we call this wave number because it is the number of waves that are packed in per unit of distance. And this is expressed in units of inverse centimeters. So the infrared region of the spectrum is from 4,000 to 400 inverse centimeters. That means 4,000 to 400 waves per centimeter. That's how many oscillations are packed into that distance. Why did they choose that? I don't know. Other than back in the day, making graphs was difficult. You had to either do it by hand or on a typewriter, and scientific notation was too painful to do, and they probably didn't have the Greek letter micro, the Greek letter M or whatever, mu, thank you. Look at that and I see micro because that's what that means in terms of units. They probably didn't have the Greek letter mu on their typewriter. So these inverse centimeter units just happen to be convenient. So when we talk about different frequencies in infrared spectroscopy, it's going to be in wave number. Notice that wave number is inversely proportional to wavelength, so that means it's directly proportional to frequency, meaning higher values of wave number correspond to higher frequency and higher energy for photons. That's going to be important in sort of understanding how the spectrum works. Now, what does infrared spectroscopy measure? The idea is that the photons that are in the IR region report on vibrational modes for bonds. So bonds vibrate, and you can model them as two masses at the end of a spring. There are a few different ways that a bond can vibrate. You've got stretching, which is just parallel to the bond between the two atoms. They're stretching back and forth. And then there is bending. where you've got maybe a bond angle here, theta, and that angle is changing as the atoms move a little bit. So stretching and bending are both possible, and infrared radiation excites transitions among vibrational energy levels. One way this might look, and some of this gets into physical chemistry, which you are welcome to take if you want to, Chemistry 460 and Chemistry 462. You'll talk about spectroscopy there, but for our purposes, it's enough to know that infrared radiation excites transitions in vibrational modes. One way that can look like is to have a bond stretching like this, and then it absorbs a photon, and then the amplitude of the stretch changes. It stretches further. And there's more to say about that, but the idea is that molecules will absorb in the infrared region, and different bonds undergo different vibrational transitions and therefore absorb different frequencies of infrared light. One thing that's useful, I'm going to write it here, and then you're going to immediately ask, do I need to memorize that for the exam? And the answer is no. But I honestly didn't really appreciate this until I started retooling some of these notes that I'm working from, and it actually helped me a lot to think about bond vibrations in this way. So here you go. You may have learned from physics that you can model two masses on a spring with Hooke's law, where the frequency or the wave number that you observe for a vibrational transition is going to relate to some constant k, which we won't worry about what that is or what it means. Not even a chuckle from you guys. What, is it too early in the morning? F is a force constant. And there are two sort of important points here. This is going to depend on the type of bond. Different bonds will have different kinds of force constants. So a couple of different principles. Stronger bonds will have larger force constants, and therefore they will have higher frequencies that they undergo their transitions at. So you would expect, for example, a carbon-carbon bond between, a single sigma bond between two carbons to absorb at a lower frequency or a lower wave number than a carbon-carbon double bond, because double bonds are stronger than single bonds. And similarly, you'd expect a triple bond, a carbon-carbon triple bond, to absorb at a higher frequency or wave number than a double bond or a single bond. Okay? So strength of bond. The other sort of aspect here in it for force constant is type of vibration. This won't matter too much unless you really get into the weeds on infrared spectroscopy, but it turns out that bending is easier, meaning smaller force constant, than stretching. So you will see that for a given kind of bond, you'll see that the stretching vibrational mode absorbs at higher frequency than the bending vibrational mode. Not necessarily too crazy. I'll show you some examples of that. Finally, and perhaps more importantly, M is the mass of the atoms attached to the spring. That's an oversimplification. You have to account for the masses of both particles, because there's two things, not just one, on either end of the spring. But in general, if the particles on either end of the spring are lower in mass, then the spring will vibrate at a higher frequency or a higher wave number. So you would expect a carbon-hydrogen single bond to vibrate at a much higher frequency than a carbon-carbon single bond, because the hydrogen is much, much smaller by a factor of 12 than a carbon. All right, so with this in mind, I want to show you some characteristic bond vibrations and frequencies for a molecule. Do you need to memorize this structure? No, please do not. This actually comes from my own research. There was a reason I needed to do some calculations on this molecule that aren't important here, but one of the aspects of those calculations is it tells me what the bond frequency, the frequencies of vibrations are for all of the bonds in the molecule. So this was done in a program called Gaussian. This stuff doesn't mean anything. It's just there so that I can. It's mostly self-indulgent. I just want to impress you. So there you go. So here are some. I learned how to make GIFs. Anyway, it's controversial, isn't it? I learned how to make those things, GIFs. Makes me sound really old. And here is a stretch between an oxygen and a hydrogen. That's an OH bond stretching. And it stretches, the frequency that bond would absorb is around 4,000 wave number, or 4,000 inverse centimeters. Okay, so that's a single OH bond. An NH bond absorbs at pretty close to that, not quite the same, but in the same region. And you will see that these are usually bonds between a heavy atom like carbon, nitrogen, or oxygen, and hydrogen absorb in the sort of 3,000 to 4,000 region of the spectrum. Here's a CH bend. What I didn't show you here is a CH stretch, but it would have happened at about the same frequency as these OH and NH stretches. This illustrates the principle I told you earlier that bending is easier than stretching, so bending has a smaller force constant and therefore a smaller frequency. But that's sort of the methyl groups, those CH bonds are sort of wagging out of their place. That's an example of a CH bend. There's others that we could look at. So, there is a CH3 stretch. That's kind of dancing. It's kind of fun. So you can see that the CH stretch is around 3,000 wave number, whereas a corresponding CH bend is much lower frequency. You will see that the hybridization of the carbon that has the hydrogen matters. That bond strength increases as you go from an sp3 carbon to an sp2 to an sp carbon. And so we'll see some characteristic stretching frequencies there that are sometimes informative. One of the most informative peaks in an IR spectrum, aside from these OH, this characteristic OH stretch, is a carbonyl stretch. You can see in this molecule, actually, the two carbonyls are sort of coupled to each other. You can see the carbon-oxygen pi bond here and another here. And they vibrate at different frequencies, though they're close enough to each other that their vibrations affect each other. These vibrations occur in the range of 1,700 to sort of 1,900 wave number. That peak, you'll see examples of that in spectra I will show you. That's a very easy peak to analyze in an IR spectrum. And that's really, if you have a carbon-oxygen pi bond, that's really useful information. This will confirm for you some things you could get from the molecular formula alone. Last time we talked about degrees of unsaturation or double bond equivalence. If you've got oxygens in your molecule and you have one double bond equivalent, start looking in your IR spectrum for a carbon-oxygen pi bond. That's a really easy way to explain that extra degree of unsaturation. Here is a stretch between carbon and hydrogen when those carbons are sp2 hybridized around 3,300 wave number. I guess I should have ranked these in decreasing order. Those are sort of characteristic benzene ring CH stretches. And then here are some carbon-carbon stretches within a benzene ring. I like these images because they demonstrate that molecules are not static like we draw them on the paper, that bonds are actually vibrating all the time. And there's no way to really get this without doing the calculations and actually showing you structures like this. You can't draw this on a sheet of paper. But One thing that's actually pretty important is to note that the carbon-oxygen pi bond stretch is at a little bit of a higher frequency than a carbon-carbon pi bond stretch, like in the benzene ring. This is because carbon-oxygen pi bonds are stronger, more stable than carbon-carbon double bonds. And so the carbon-oxygen double bonds absorb at higher frequency. Also, you will see that not only are we going to be looking at the frequency at which a peak appears, but also the overall shape and intensity of a peak in a spectrum. And they're often, the carbon-oxygen pi bond peaks are much sharper and stronger than the carbon-carbon pi bond peaks. So here is what an IR spectrum is going to look like. We generally are going to limit ourselves to worrying about the portions of the spectrum that absorb, the peaks in the spectrum that absorb from about 1500 and beyond. This is what we call the functional group region of the spectrum, where there are characteristic peaks that are easy to interpret. Down below 1500 wave number is the fingerprint region. This is very difficult to interpret because it's different for every molecule, and it involves not just single bond vibrations, but vibrations in coupled parts of the molecule that are sort of non-intuitive. You can calculate them, and that's fine, but it's not like you can look at that portion of the spectrum and say, oh, I know what that is. Okay, so you can see some things that I told you earlier. Stronger bonds have higher frequencies, so carbon-carbon single bonds, double bonds, triple bonds. In that order, higher frequencies, stronger bonds, stronger force constant. Also, you see what I said in terms of mass, right? That if your bond involves a hydrogen, your frequency should be higher. So all the stuff roughly from 2500 or 3000 and higher is going to involve hydrogens, okay? All organic molecules have hydrogens. So this part of the spectrum could be pretty busy. Nevertheless, there are some key features that are pretty straightforward to interpret. So I'll show you a table that your text gives you it sort of summarizes the information that's here in this schematic of a spectrum. But we'll talk about kinds of bonds, we'll talk about sort of what their characteristic wave numbers are, and then we'll talk about general features of a peak in an IR spectrum. The OH bond generally shows a peak in the range of 3600 to 3200 wave number. We're going to describe peak intensity, that is how high up the peak goes, with words like strong or medium or weak. We'll describe the peak shape with words like broad or sharp. The OH peak is generally broad. It's maybe the broadest peak that you will see. I showed you an NH peak or an NH vibration earlier. This occurs in the same range of frequencies that an OH peak occurs. However, its shape is different, and that's one of the ways that you can tell. Generally, the intensity is medium for an NH group, but I put an asterisk on there because if the NH group is part of an amide, which is a different functional group, it can be strong and sharp. I'll show you some examples of both of that a little bit later. CH bonds also vibrate in this region of frequencies, though it depends on what kind of CH bond. If it's an sp3 CH bond, an sp2, or an sp CH bond, it changes a little bit. 3000 to 2850 is for just a regular sp3 bond. Generally, the peaks are strong not particularly sharp because there are many overlaid peaks. So I'll show you examples of that, but it can be kind of messy. For molecules with just a few or one sp2 hybridized carbon-hydrogen bond, these tend to vibrate at slightly higher frequencies, so they'll be separated from the cluster of peaks that represent an sp3 hybridized carbon-hydrogen bond. They tend to be pretty low in intensity, but they also tend to be pretty sharp. I'm putting an asterisk here because for aldehydes, things change quite a bit. So I'll show you some characteristic stuff about aldehydes. For an alkyne, like an sp hybridized carbon-hydrogen bond for a terminal alkyne, those vibrate at even higher frequencies. Again, the intensity is medium, but the peak is sharp and separated from the cluster of peaks that represent the other CH bonds in the molecule. So that can be useful. Let's see, I told you about carbon-carbon triple bonds. These, because they involve carbon and not hydrogen, these vibrate at lower frequencies. A lot of the carbon-carbon types of vibrations are medium peaks, but are sharp. A carbon-nitrogen peak, as in a nitrile, also absorbs in this region with the same general shape. A carbon-oxygen double bond has a characteristic set of frequencies from like 1800 to around 1650. This is one of the easiest to recognize. Carbon-carbon pi bonds, as I said, absorb close to the same region, but are weaker. And then we could include in the carbon-carbon double bond the benzene rings. These tend to absorb, there tend to be multiple peaks for a benzene ring, and these tend to absorb in the same general area as the carbon-carbon double bond, though at slightly lower frequency. Well, I'm trying to write the same thing twice. They should also be sort of medium and sharp. All right. So here is an IR spectrum of a molecule, and we can use the information in this spectrum to determine whether this molecule is A, B, or C. Often it's not only what peaks that are there, but also what peaks are not there that tell you some important things. To get you oriented to the spectrum, notice that lower numbers appear to our right and higher numbers appear to our left. Don't know why that is, just tradition. Second, the y-axis is something called percent transmittance. That means how much light is getting through. So a peak corresponds to something that has closer to 0% transmittance. That means light is getting absorbed. Now, if you've had 107, you've talked about absorbance before. You can calculate absorbance from percent transmittance. You might ask, why didn't they put absorbance here? In that case, the peaks would be 0 here and then go up to high absorbance here. So they're sort of backwards. I don't know, I didn't invent it, but this is just the way it is, and you're going to have to get used to it. So a peak corresponds to something with less than 100% transmittance. If it's 100% transmittance, all the light at that frequency is getting through. If it's 10% transmittance, that means only 10% of the light's getting through. Why? Because your sample is absorbing light. All right. So looking at the features of this spectrum and the table that's sort of above, this is easier to interpret if we look at what we would expect for these molecules. So for molecule C, which has an OH group, we want to be looking for, go to your table, a strong broad peak in the range of 3,600 to 3,200. I will show you later what an OH peak looks like, but this is not that. The OH peak, if it were there, would take up perhaps this much space. So what we see here is not an OH peak. That automatically rules out C as an option. Okay, let's talk about B. The key feature on our list of B would be, notice how that because I didn't even see the OH peak, I didn't even worry about the carbon-carbon pi bond. Also, all of the molecules have carbon-carbon pi bonds. So if I want to distinguish between them, looking for differences there is silly. For B, I have a carbon-oxygen double bond. I expect a strong, sharp peak in the range of 1650 to 1800. I do see a peak at around 1650, but 1650 to 1800 would be here, and in general, peaks corresponding to carbon-oxygen double bonds would be much deeper, much stronger, and a little bit broader than this smaller medium peak. This size peak corresponds to medium. Percent transmittances in the sort of 60s to 70s, that's sort of medium peak. A peak that would have percent transmittance in the 80s to 90, down at the sort of 20 to 10% level, that's what's called a strong peak. So we also don't see a carbon-oxygen double bond. So that means it can't be B, it's probably A. Let's look at the features of the spectrum and how they agree with what we expect. For a carbon-carbon pi bond, we expect absorbance of a medium intensity sharp peak at around 1650. That's exactly what we've got here. So this would correspond to the carbon-carbon double bond stretch. Notice how I'm not worried about anything below 1500. Then as I go up to slightly higher frequency, this cluster of peaks that are strong and sharp but are overlaid with each other correspond to roughly the region I expect for an sp3 hybridized carbon-hydrogen bond. And you'll get used to seeing that and saying, oh great, I have carbon-hydrogen sp3 hybridized CH bonds. Yeah?
Do you need to have this table of bonds memorized?
Do you need to have the table memorized? No, you'll have it on the exam. You should be familiar enough with it to use it, though, that you're not basically starting from first principles. The way I say it is this. I know that when I read music, I know that every good bird does fine and all cars eat gas or whatever, and FACE and all of that stuff. But if by the time I'm playing a solo, I'm still reading the notes, I'm going to have a hard time. So you got to be familiar enough with it that you're not sort of going back to first principles. Yeah. Another hand. Yeah. Yes, it is, because the carbon-carbon single bonds, most of the heavy atom single bonds all happen in this fingerprint region of the spectrum. Difficult to interpret, yeah. Fortunately, that's the boringest part of an organic molecule in the sense that all organic molecules have single bonds. Yeah. Yes?
So you wrote on there that the carbon-carbon double bond was a stretch. Do we know how to tell the difference between a stretch and bending?
No, we don't. And in fact, that's not even distinguished here in the table. Most of these are stretches. Okay. Yeah. I made that distinction up here just to show you that stretching and bending has slightly different frequencies. Okay. But notice that this bend is going to be in the fingerprint region of the spectrum anyway, so difficult to interpret. Yeah, so a lot of the CH bends are going to be down here. Most of all of this is all stretching. Okay, yes?
We wrote that the NH bond is medium unless it's angled.
Yeah.
And strung sharp.
Yes.
But what's the shape if it's not?
Both of them tend to be, well, if in general it tends to be broad. I'm going to put a broad-ish because it's not as broad as the as the OH group. I'll show you examples of all of these. Yeah. Okay, the other feature that you might be inclined to pass over if you were in a hurry is this one peak that's a little bit to the left at higher frequency than these sp3 CH stretch peaks. That corresponds to my sp2 hybridized carbon-hydrogen stretch peak. And as I look, I have two sp2 hybridized carbon-hydrogen bonds there. So you can look for those on alkenes that have hydrogens, and they should show up at just a little bit higher frequency than your characteristic sp3 CH bonds. Okay, so this can be useful in narrowing down the range of possibilities when you're trying to solve the structure. I'll take you through some examples. Here is another spectrum, and I'm not showing you the structure of the molecule or even giving you any possibilities. We just want to get used to looking at the peaks. To the left of the fingerprint region, I see two major sets of peaks. What you're looking at here at around 1700 wave number is a classic carbonyl stretch. You ought to get used to seeing that and looking at it. You can see that that's much different than the spectrum above, where we had a CH stretch at 1650, but it was much less intense. It is possible to get these confused. When you're, at least early on, when you're inexperienced, you're going to look at that and say, ooh, I wonder if that's a carbonyl. Resist the temptation. Carbonyls will always have percent transmittances that are close to like 20 or 10%. So a peak that's this small is not a carbonyl. And then, of course, you know, you've got this peak again around 2,900 to 3,000 wave number or inverse centimeters. This is a sp3 carbon hydrogen peak. We don't know very much about this molecule. We know it's got CH bonds and we know it's got a carbonyl. But that can be enough plus other information to give us to help us solve the structure. All right, looking at this one, again, ignoring anything to the right of the fingerprint region, I see two major features. One is a peak that's around 2250 wave inverse centimeters. Again, you will be tempted to say that's a carbonyl. Pay attention to the frequency. The frequency for carbonyls is 1650 to 1800. This is at too high of a frequency to be a carbonyl. But if you look at our table, the 2250 region is where we expect triple bonds. So this could be either a carbon-carbon triple bond, or it could be a carbon-nitrogen triple bond. We don't know at this stage. We would need additional information from other sources to be able to distinguish between those. We see again here the characteristic sp3 carbon hydrogen stretch. One thing we don't see, so if it were an alkyne, we would expect, and it were a terminal alkyne with a CH bond on it, we would expect to see something, a medium sharp peak at around 3,300 inverse centimeters. We don't see any medium sharp peak here. So if it is an alkyne, it's not a terminal alkyne. Yeah?
Didn't we think that the triple bonds were medium?
Yes, we said that they were medium. I guess there's some context there. That might actually distinguish between a carbon-carbon or a carbon-nitrogen. It's possible this is a nitrile rather than, and again, I guess you're seeing that these terms are necessarily qualitative. So there is a little bit of wiggle room and you'll have to sort of learn by experience.
It's the trend, but there's usually some variance.
Right. Right. In other words, I can't really point. Generally, when we say medium, we're talking around 50% or less transmittance. This appears to, I'm only writing down, if you go to your book, it tells these things. It says these things in the table. So that's really no excuse other than that there's some variance. Yeah. Okay. Let's see. Oh, well, I think we've already done one like this. Here, the major features again to the left of the fingerprint region are this one. This is around 1600 wave number, or 1600 inverse centimeters. That combined with this peak that's around 3100 suggests to me some kind of alkene. You've got both a carbon carbon double bond type stretch where you would expect it. And then you also have an sp2 hybridized carbon hydrogen stretch at around 3,100 inverse centimeters, in addition to the characteristic sp3 carbon hydrogen stretch. Yeah?
So does this like speak at all to the quantity of this kind of bond, like what we see?
Yeah, it's a good question. Would this tell you at all the quantity of a bond? In other words, sort of. I mean, you can tell there's probably more sp3 hybridized carbon hydrogen bonds than there are sp2 hybridized carbon hydrogen bonds, but there's no quick one-to-one correlation. Later, when we get to nuclear magnetic resonance spectroscopy, and by later I mean Wednesday, you will see that the area encompassed by a particular peak is related in that experiment to the number of hydrogens that peak represents. Not so here. Yeah. All right. So let's just show you some examples of key functional groups, and then we'll work on a problem. Then I'll show you a problem where we're going to use some of this information to get, use some of the information in an IR spectrum to determine the outcome of a reaction. So here is hexane. Nothing to see here, folks, except for the large peak for CH bonds at around 3,000 inverse centimeters. In the fingerprint region and below, the only thing this can be is carbon-carbon single bond vibrations. There's not that many of them because hexane's a simple molecule. Make it hex 1-ene, where there's a single double bond, and compare those two spectra. You see the new presence of a peak slightly just on the left-hand side of the fingerprint region, corresponding to a carbon-carbon double bond. You see the characteristic sp3 CHs, and then this one sp2 CH separated and small in intensity. And again, that's not, if you knew this were some kind of hexene, but you didn't know which one, you didn't know where the double bond was, this peak would absolutely tell you where the double bond was. So that can be useful information. Any other isomer of hexene where the double bond is somewhere in the middle, oh, well, forget that, scratch that. I didn't think that one through. Do you see why I'm wrong? Internal double bonds have hydrogens on them too. So actually, the presence of this peak doesn't actually tell us whether we're looking at hex 1-ene or any of the other regioisomers. And so you can see the limits on what IR spectroscopy can tell you. It can tell you that a double bond is present. It can tell you that there are hydrogens on that double bond. It can't tell you the connectivity. That's a limitation. That's why we're going to talk on Wednesday about NMR spectroscopy, which will give us connectivity information. All right. You can see now how the alkyne differs from the alkene. For the alkyne, I see a medium, and this is a case where now it really is a medium peak, right? Instead of being quite intense for the carbon-carbon triple bond. I see a lot of sp3 carbon-hydrogen bonds, and then quite separated from that, and perhaps more intense than I expected, I see an sp hybridized carbon-hydrogen bond. So there is some variance there. Let's see, others, so here is an OH group. Sorry, here is butane 2-all. And you can see what I mean by broad and characteristic. If you've got an OH group, it basically spits in your face and says, hey, look at me, I'm an OH group. This large, curved, broad, and very low percent transmittance peak, generally decently separated from the sp3 hybridized carbon-hydrogen peak. That's a dead giveaway for an alcohol. That'll come up again and again in 353 if you take that class, so you ought to be aware of this. Here's the corresponding, I believe this is an isomer, same molecular formula, but no OH peak. All you've got here is the sp3 hybridized carbon-hydrogen bonds and the fingerprint region. This is the ether. This is an ether. Ethers actually are really hard to identify by IR information alone, because all you've got is that, oh gee, there's CH bonds, and then a bunch of stuff in the fingerprint region. But again, the lack of the OH peak and the lack of a carbonyl peak does sort of limit you on the possibilities for what that molecule could be. Here is an aldehyde. There's some weird things going on with the aldehyde. Here is the characteristic carbonyl peak. There's a cluster of peaks here that are in the region for an sp3 carbon-hydrogen bond. There's also two peaks that are sort of separated at much lower frequency than expected. Those correspond to a CH bond. I've never really worried about these, just this time as going through I noticed them and thought, gee, that's kind of weird. I can't remember any time in my past when anybody has ever asked me about the CH stretch of an aldehyde. So here you've seen it. If you need to come back and look at it, go for it. As I said, having never been asked about that information before, you can guess whether or not I'm going to ask about it on the exam, which is not. Here is butane 2-one, characteristic carbonyl peak. Here's a carboxylic acid. You can tell those because they will have both the carbonyl and the OH. And in general, for carboxylic acids, the OH peak will be broad and it will actually encompass the CH peak, which was different than for a simple alcohol. For the simple alcohol, there is separation between the two. For the carboxylic acid, there's generally not. A couple of more things. One of the ways you can distinguish an acid from an ester is that the ester will lack the OH peak. So here I've got the characteristic carbonyl peak, here no OH peak. And then I think these are our last two examples before we do a practice problem. Here is an amide. An amide will have the carbonyl peak, and then it will have two very strong and sharp NH peaks. At least this one will, because there's two NH bonds. For an amine, those peaks are much smaller. And that has to do with the strength of the bond and the properties of amides versus amines. You can see, therefore, that amines and amides are more difficult to interpret than OH groups because there's a lot more variability in what you can expect. All right, with that, let me just point out that you can use IR spectroscopy to monitor how well a reaction has proceeded. In this oxidation reaction of a secondary alcohol, an OH group is changing to a carbonyl. That should cause the disappearance of that large, broad, strong peak at around 3600 wave number, 3600 inverse centimeters for the OH group. And we should see the appearance of a peak at around 1700 inverse centimeters for the carbonyl group. You can actually take samples of a reaction, run them down to the IR instrument, and watch that happen. And then you know the reaction's over when your OH group disappears. That's highly useful information. Also, you can use this information to rule out various possibilities. So, I give you a mass spectrum, an IR spectrum, and I tell you only that the molecule has carbon, hydrogen, and oxygen. You know what the molecular ion, you know what the molecular weight is, you don't know the molecular formula. And you know from the IR spectrum that you're going to have carbon-hydrogen bonds. Great, that's informative. And then a carbonyl group. That may be useful. So let's show you how you would sort of try to tease some of these things out. First thing you do, if all you've got is a mass, is you figure what's the max number of carbons I can have in this molecule. So that's 7 carbons with a remainder of 4. So my first potential formula is C7H4. Now, already you can see that that's too many carbons for not enough hydrogens at that level. If you don't believe me, calculate the degrees of unsaturation on that thing, and it ends up being like 6. You need 6 double bonds or rings with 7 carbons. Not that reasonable. So you start to try to tease this out by saying, okay, what if in this formula we replaced one of the carbons with 12 hydrogens? We'll still get 88 molecular weight. That would be C6H16. That's also unreasonable. If you calculate double bond equivalence or degrees of unsaturation there, you get -1, which tells you you have too many hydrogens. So what am I going to do? Well, I can't replace carbons with more hydrogens. So what if instead I start replacing 1 carbon and 4 hydrogens with an oxygen? The math adds up. 16, the CH4 is 16, and oxygen is 16. Then I start to come up with C5H12O. I can calculate double bond equivalence for that. If you did that, you would see that it's 0, which seems like a reasonable possibility, except the IR data says I have a carbon-oxygen pi bond, so that's not the right molecular formula. Let's do it again. Let's take another CH4 and replace it with an oxygen. Then the formula is C4H8O2. Double bond equivalents there are 1, so that's a reasonable possibility. Now, I'm going to show you a bunch of potential structures that have that formula, C4H8O2, and we can talk about which of these might be consistent with the data and which are not consistent with the data. That's a methyl group, by the way, not a negative charge. All of these obey that molecular formula. Okay, looking at the data, which ones of these do you want to rule out? A, B, C, or D? C and D, right, no OH peak, boom. Now, you still can't tell the difference between these two esters with the IR spectrum, nor are you meant to. You need more data for that. But eliminating other possibilities is also highly useful. Okay, so I think that about takes us through to the end of spectroscopy B. Next time on Wednesday, we will jump in on spectroscopy C.